I am Sungwon Lee from Hanyang University. This is a joint work with Donghyun Cho, Jiwon Kim, and Taehyun Kim. I will present our work Restore from Restored, Video Restoration with Pseudo Clean Video. It is known that self-similar patches tend to repeat many times across several scales within a natural image. This property is called patch recurrence. Many image restoration works such as super resolution, deblurring, and denoising show that better image quality can be restored by using this internal information. Recent self-supervised denoising methods such as noise-to-noise, noise-to-self, and noise-to-void train denoising network without ground truth images. The network optimized by these methods can remove noise in input noisy images under an statistical assumption. Naturally, they exploit self-similar patches within noisy images during training. Generally, there is a much larger number of self-similar patches in a video rather than a single image. For example, we can see multiple self-similar patches of white field line in neighboring frames. As self-similarity is beneficial in image restoration, performance improvement for video restoration can be achieved by using this property. To exploit these self-similar patches, recent video denoising method, called frame-to-frame, extended the noise-to-noise method to handle video frames. Frame-to-frame searches for self-similar patches among neighboring noisy frames using optical flow, and then apply the noise-to-noise method to minimize the difference between a noisy frame and the warped previous noisy frame. In this way, frame-to-frame can fine-tune the pre-trained video denoising network at test time, and show effective blind denoising performance. However, frame-to-frame depends on accurate optical flow estimation, which is difficult and challenging under some corrupted conditions. Moreover, when the pre-trained network is fine-tuned with noisy patches, the fine-tuned results given corresponding noisy patches become an average of self-similar noisy patches. To avoid dependence on optical flow while exploiting self-similar patches at test time, we propose a new adaptation method, Restore from Restored, which also updates the network parameter at the test stage. Our method fine-tunes the network to obtain an average version of denoised self-similar patches existing in neighboring frames. First, we generate a pseudo-clean frame, which is an initial denoising result by the fully pre-trained denoising network. Next, we generate a pseudo-noisy frame by adding a random noise to the pseudo-clean frame under an assumption that distribution of input noisy frame is similar to that of the pseudo-noisy frame. Using these pseudo-training set, we can adapt the pre-trained network during test time to the specific input noisy frame, by minimizing the network output from pseudo-noisy frame in the pseudo-clean frame. In particular, when the baseline denoiser is a fully convolutional network, we don't need to search for self-similar patches during adaptation thanks to the translation equivariance property of the fully convolutional network. Consequently, when differently corrupted pairs of self-similar patches are exposed multiple times during the adaptation, a fine-tuned fully convolutional denoiser can output an average of the denoised self-similar patches. In our work, we propose online and offline adaptation methods. In online method, we use previously restored frame as a pseudo-target and its noisy version as a train input. In offline method, we use all the given frames in a video, and can more improve denoising performance than online method. Our adaptation method improve baseline performance in both online and offline mode. Especially, we can achieve more improved results with offline algorithm, and it shows consistently increasing performance as fine-tuning steps are iterated. Table shows two state-of-the-art video denoising networks can obtain better results on a video corrupted by various Gaussian noise levels. Both online and offline approaches elevate the baseline performance by a large margin. Visual results show that our method can effectively recover tiny repeated patterns.